Hi, okay, let's do what might be my favorite section of this entire class. Okay, let's talk about logic. All right. Okay, we're going to take word statements and then we're going to turn them into math problems and then we're going to solve them with something called a truth table. It's pretty cool. Let's get going. What we're going to be talking about is something called Boolean logic. It's a branch of algebra, and basically it is the crux of how your computer makes decisions, how your computer even runs. Boolean logic is based on the idea that there are only two answers. It's either true or false, and that can be translated to zeros and one, and that's why computing is based on Boolean logic. Now we solve we solve logic problems with Boolean logic and using their operators and truth tables. And truth tables are going to be a tool that you're going to be provided with that will assist you in organizing the possible outcomes so that you can make a informed and well-reasoned decision using logic. There are operators in Boolean logic, and just like there are operators with sets, they are kind of related exactly to sets that you've used kind of in the past. So we have the intersection. Let me get a pen going here. We have the intersection, and for sets and everything here that's not bolded is sets, and everything here that's bolded is Boolean logic. So for sets, we have the intersection, which is the upside down U, right? And that's everything that's in both sets. It's in the intersection. In Boolean logic, we call it and we also call it the conjunction. And instead of using this upside down U, we use this little A without the bar. Okay? That's the symbol that we use. And then for the other one, the union, where we put the two sets together, whether it's in set A, set B, or in the intersection, it's always in the union. That is for an or statement. It's either in set A or it's in set B or it's in both. And that's called a disjunction. And we use this V shape. And then the complement, we dealt with complements before. And here we're going to call it the not. It's called the negation. And the symbol we use here is called the tilde, the little squirrely thing that's all the way on the top left-hand side of your keyboard next to your one. It's even shifted and that whatever the heck that accent is up there. Okay. All right. Another thing that you need to know is once we have our Boolean logic equations written out, that they follow and you must read them from left to right. And we observe parentheses as an order of operations. So if you come across something with parentheses, you must figure that guy out before you can proceed. Okay. So in logic, we have statements. And then we have compound statements called conditionals. Okay, so statements are very basic and they are either true or false. And a conditional is made up of statements and of the form if P then Q, or maybe if P then Q else S, something like that. Okay, now this sounds crazy, but this is straight up math. I know this sounds a little bit crazy, but I want to make sure that you understand that conditionals are like a statement. Okay, statements are just straight across. Generally, ands and ors are statements. Okay, so statements, this is going to be ands and ors. And then the conditionals are going to be the conditional. It's called the conditional and the biconditional. I know the language here is really, really confusing, okay? And I'm really sorry that it is. I didn't make it up. I would have called things differently. But we have statements, and statements are either true or false. And a conditional is a compound statement, okay? And we'll find that those are either going to be true or false depending on the issue. We're going to have to kind of baby step our way in here, all right? Now, I have a little example down here. I said a conditional could be if P, then Q, else S. Let's read my little statement here. It says, if it's raining, we will go to the movies. Otherwise, we will go to the beach. So this is if P, then Q, else going to the beach is S. So you can see there that I spelled else wrong, but you can see there that that's how that could kind of come across. So let's see how we can do some more here. Statements describe an entire set, and there's two types of statements, okay? So there's something called a universal quantifier, and a quantifier is a word that describes a quantity. So quantifier. A word that describes, oops, why did it do that? A quantity. And there we go. Okay. Now, universal means that you're going to use words like none, all, every, something applied to each. Okay. And then an existential quantifier is something that is applied to at least one. Not applied to all. At least one. It could be none. It could be a few. It could be several. Okay. So let's look at a couple of statements I have here. So this first statement says everybody cheats on their taxes. And I say, how can you disprove that? So what is a statement that we could say that could disprove everybody cheats on their taxes? Would it be that, would we have to check with everybody and be like, did you cheat on your taxes? Did you cheat on your taxes? Did you cheat on your taxes? Would we have to check every single buddy? Or would it be enough if we just found one person that did not cheat on their taxes? That's true. What disproves a universal quantifier is an existential one. So if somebody says all, you only have to show one instance that it might have happened to disprove what their statement is. But if somebody says one, then you have to check all the others to make sure it couldn't possibly happen again. That's kind of the idea here. So back to example one. Everybody cheats on their taxes. The disproving statement for that would be, so it says everybody. So we would say at least one did not cheat on their taxes. It only takes one, right, to do what they say they're not doing. Right? They said everybody cheats. Well, then at least one doesn't cheat. Does that make sense? So you're going to go from a broad everybody to at least one and doesn't do whatever it's saying that they're doing. Let's look at the next example. One of these 6 cartons of ice cream is melted. How can you disprove this? Well, you would have to check. You'd have to check. You would have to say none of these 6 cartons are melted? After checking each one, right? You'd have to check them all. Y'all don't get lost here. Hang on. I know it seems kind of crazy. I wrote it out for you in a nice way that you can kind of understand. Please be free. Please feel free to pause and really understand these. But let's take a look here. This says the negation of all A's are B. So all A's are B are at least one is not a B. Okay, just like our last example. So the negation of no A's are B, saying none of you people are paying your taxes. Say at least one is paying their taxes. So if we've got none, at least one is. So none are, at least one is. All are, at least one is not. Okay, these are the universal ones. Universal means applies to all of them, right? It's kind of easy to remember those. And this is the existential. Okay, the negation of at least one is none of them are. And the negation of at least one is not is all of them are. All right, so let's find the negation of the following statements. Somebody brought a flashlight. So what's the negation of somebody? First off, is somebody universal or existential? Somebody is existential. Okay, so we need to negate it with a universal statement. Okay, so if somebody brought a flashlight, then we're going to say somebody, at least one is, nobody brought a flashlight. Right? The opposite of somebody is nobody. Somebody brought a flashlight, nobody brought a flashlight. So it negates it as well. Okay, let's look at this other one here. All prime numbers are odd. All is a universal quantifier. So all prime numbers are odd. This is all RB. This is the situation we are in with our example number 4. All RB, so we could say at least one prime number is not odd. And we know that, in fact, it's the number 2, right? Okay. So now let's take the words and turn them into symbols and make this look a little bit more like math. Okay? All right, so keep in mind that if I say and, I mean a conjunction, and that is the little caret looking thing, the capital A with no line through it. And if I say or, the disjunction, it looks like a V. I look at it like a really sloppy R, and that's how I think about it. I think about it like a sloppy R. If I was like A-R-E, sloppy R. Not a stoppy R, a sloppy R. Okay, anyway, let's get back to this. Sorry. I'm really sleep deprived, so I'm hoping I may even make it through this. All right. So let's let P, the letter P, be I like Pepsi, and let's let the letter C be I like Coke. And I want to write I like Pepsi or I like Coke in symbols here. And so I like Pepsi or I like Coke. That's it. Okay. I like Pepsi and I like Coke. I like Pepsi and I like Coke. Awesome. I do not like Pepsi. Remember, not is the negation, and we use the tilde. Okay, so this would be I don't like Pepsi. This one says I don't like either Pepsi or Coke. Now, this part right here lets us know that we're going to have a tilde, right? But this is a compound statement, Pepsi or Coke. So we'll have a parenthesis here, Pepsi or Coke, and then we'll put the negation in front of that. So that is, I don't like Pepsi or Coke. And then the last one is, I like Pepsi and do not like Coke. And that would be, I like Pepsi and not Coke. Okay. All right. So that brings us here to this crazy looking business. These are truth tables, and truth table is a tool to help you see complex truth values. All right, and they're based on statements like ands and ors, and we'll also be looking at the conditional and the biconditional, and oh, of course, the negation. Okay, so these are the three basic truth tables that we're going to start off with. The first truth table here, A and B. Okay, so that's the intersection. I'm going to write the word and up here. So you know, it's either in A and B. This is for the or, and this is for the not. Okay, now let me tell you how to read this, because that's the hard part here. So we have two columns. And then we have these rows. The first column is for A, second column for B. And in fact, if we had more variables, we'd have that many columns across. And we'll see that as we go on. But we're going to start off very straightforward here. So we have A and we have B. And what the body of the table gives us is all of the ways that we could mix two variables with two outcomes, either true or false. And that's just a way, it's a pattern that you'll write down. And then this over here is the output of the truth table. In this particular truth table, as you see, if we have true intersect with true, you get a true. If you have true intersect with the false, you get a false, because what does and or the intersection mean? It means that it's in both, right? So be sure that you also remember that and is the intersection. If those ideas stick with you well, and or is the union, right? Just in the set or in the intersection of the set. That's the two differences. Okay. And so I'm going to show you on the next few slides how you will set up these tables. You will set up the A and the B in a pattern that I'm going to show you that you will always use. And then you can lean back on these basic truth tables to finish the rest of your problem. And you're going to see that as we go on. It's kind of hard to explain until we get into it. So let's take a look at this. Create a truth table for A or not B. So pay close attention here, and I'm going to be crossing these guys out because you don't need to make 3 truth tables to do it. This is the only one that we need, but I need you to understand how we got there. So this is the basic. This is the basic setup. No matter what it's asking you to do, if it's just 2 variables, this is how you're going to set up every single time. Your first row or your first column is going to be A, and you're going to list it as 2 trues, then 2 falses. And then your second column is going to be B, and you're going to list it as true, false, true, false. What this does is it captures every possible outcome of the true and the false and all the possible mixes and all the combinations. I don't mean to provoke you from your probability from last time, but it's combinations of outcomes. Okay? That's how it all comes together. So this is your setup. Not given to you. This is what you set up, okay? Now, this particular question is asking us to find A or not B. And for us to find A or not B, we need to figure out what not B is. So sometimes you have to do other pieces before you can put it together. So the first thing I'm going to do is find not B. Now, how do I find not B? Well, not means you change whatever the outcome is. So if B is true, then not B is false. If B is false, then not B is true. If B is true, not B is false. And if B is false, not B is true. We're just going to fill in these little table right here. Okay. Now, I'm going to draw real quickly the A and the B tables because I should have thought better about this. And when I teach them in class, I draw them up on the chalkboard or on the whiteboard, and so I can refer back to them. Oops, sorry. But I wish I had. Anyway, so this is how you set them up all the time. True, true, false, false, true, false, true, false. Okay. And now I know what the table says here. So this is true because it's an A or B, right? And to be an A or B can be in either one. It's not the intersection here. This is the A or B. So it could be true or false is true. It's not in A, but it's in B. It's still true that it's in A or B. If it's not in A and it's not in B, it's surely not in A or B. Okay, so here's our basic truth table for this guy. Now, I'm going to let you have the truth tables. I don't know what I'm saying here, truth. I'm going to allow you to have the truth table on the final exam. It'll be part of the stuff that I provide for you for formulas and stuff on it. Okay. So now what we're going to do is we're going to come back here and we're going to do this right here, A or not B. So that means that we are going to look at A and we're going to look at not B. And it's very important that you do this in the appropriate direction, okay? So we have A or not B. So we're going to be looking from here to here to figure out this last piece. And we're going to use the or. That's what this table is. This is the outcomes of the OR. So we're going to say true, false. A true, false gives us a true. So that's true. A true, true. True, true is true. That's true. A false, false. Remember, these are the two rows we're dealing with, A and not B. So false and false, that false, false is false. And false, true is true. And so this is weird, but this is the answer. The solution is that column of your truth table. All right, let's do another one. Okay. So let's set up our little table first. So we go straight down underneath the A's with two trues and two falses. And then we go straight down the B's with alternating true, false, true, false. Now this asks us to find not A and B. So let me just give us the really quick A and B. Okay. So we got true, true, false, false, true, false, true, false. This means the intersection. So if it's true in A and true in B, it's true, it's in the intersection. If it's in A, but it's not in B, it is not in the intersection. And if it is not in A and it is in B, it is not in the intersection. If it is not in A and it's not in B, it's definitely not in the intersection. So there's the table for that guy. Okay. Now, let's come back over here. You do want to work your business in order, right? So sometimes it's really helpful to kind of take a breath and look at it and make sure you set your table up correctly. We're, of course, not going to stick with just two little things here. We're going to do, bigger ones here. So the first thing we need to find is not A. So here, if A is true, then not A is false. If A is true, not A is false. If A is false, not A is true. If A is false, not A is true. Okay? And now we're going to be putting these two guys together, but it's not A or B in this direction, because direction matters. Might not matter specifically in this guy, but it certainly matters with the or, so you need to pay attention to it all the time, okay? So we have false and true. So false and true is false. False and false. False and false is false. True and true. True and true is true. True and false. True and false is false. Again, this is the solution. Now, as we go further, we're going to be making decisions based on what our truth table tells us, but we're not getting there yet. We're going to learn how to work the truth tables in this unit. Okay, let's do another one. Now, remember what I said. I said that parentheses are like operators. Sorry, got an itch in my ear. Parentheses are like operators like in algebra, and so you have to do the stuff inside parentheses first. Okay, so let's take a look here. So we're asked to do not A and B or not B. Okay, so that's what we're doing in it. And taking a look, we see we're going to have to know what the not A is, and then we're going to have to know what the not A and B is, and we have to know what a not B is before we can put it all together. Okay, so first things first, I'm just going to do my nots over here. So let's do our not A's. So that would be false, false, true, true. Let's do our not B's, which is going to be false, true, false, true. And now let's put not A and B together. And let's do this again. A, B, A, and B. And that means the intersection, right? That's the intersection. So if we have true, true, it's true in the intersection. If it's true in A, false in B, it is false in the intersection. If it's false in A and true in B, it is false in the intersection. And if it is false in A and false in B, it is false in the intersection. So this is what we'll use for this piece. So we have A and B going that direction. So false, false is false. False, true is false. True, false is false. True, true is false. I mean, true. Sorry. And now we need to know our A, our B, our A or B. So if it's true in A, true in B, it's true in A or B. If it is true in A, false in B, it is still true that it's in A or B. If it's false in A, but true in B, it is still true that it is in A or B. But if it is false in A and false in B, it is false that it is in A or B. Okay? Got to keep those guys straight. That's the key here. All right, now what are we putting together? We're doing this guy and not B, and looks like we're going this direction again as well. All right, so false, false is false. False, true. So false, true is true. False, false is false. And true, true is true. There's our solution. Okay, let's give you another one. I want to point out a couple of things about this one. This has got 3 variables in it. When you hit the 3 variables, when you set up your truth tables here, notice instead of going true, true, false, false for A, you're going to do 4 trues and 4 falses. You're going to split that in half, okay? You're going to have however many minus 1. Well, it's hard to explain it. Sorry, I'm too tired to explain it. Hold on, let me see if I wrote it down here. I hadn't been looking at my notes. Let me see if I wrote. Oh, well, while we're paused here too, seeing as I haven't been looking at my notes. While we pause here, let me give you today's silly phrase. And the silly phrase today is that clouds gossip about airplanes constantly. The clouds, they gossip about airplanes constantly. Okay. So let's get back here. Once you see the pattern, once you start making these on your own, you'll see the pattern. But if you have 2 variables, then you're going to go 2A, 2 trues, 2 falses. When you have 3 variables, you're going to go 4 trues and 4 falses. And then your next row is going to be 2 trues, 2 falses. And then that last row needs to be alternating. So in other words, if there were 4 of them here, if we had a D here, the D would be alternating. The C would be 2 by 2. The B would be 4 by 4. And the A would then be 8 by 8. Anyway, you play with it and you'll see what I'm saying. If you have any questions, certainly holler at me. Okay, so let's see here. First things first, we need B or C. Okay, and B or C. The end part for or has to be in one or the other is true, 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 false. And the and A and B, I'll just write it like that, is true, false, false, false. Right, because it has to be in the intersection of both. So it's only happens when both of them are true. I've just kind of, these are the final columns. Let me show you. They're just the final columns here. I've just shortcutted it and just wrote the final columns down. Okay, that's what this is. Okay, it's just to keep me from writing this 500 times. I should have copied and pasted a bunch of them. Anyway, so here we are. So the first thing we need to find here is B or C. So we got B or C, and we're going this direction. So, or is all true except for when they're both false. So we got true, 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 false, true, 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 false. Okay. Now the next step asks us to not it. That means find the complement of it. So this is now just means do the opposite. False, 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 true, false, 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 true. And then finally, we're going to put A together with the not. These are the ones that we're doing here. Okay. And we're putting them together with an and. So this one right here. So the only one that gets a true is if they're both true. So this is going to be false, 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 true, false, 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 false. And there's our solution. One place was true. All the rest were false. Okay. I'm going to take a quick break. Let me check on my mom, and I'll be back in a minute. Okay, so let's pick up now at the conditional and biconditional. Now, the conditional is going to become more important, even more in our next lecture. We're going to kind of like hone in on some situations with the conditional. We won't do very much with the biconditional, but it's worth seeing them and just kind of playing with them a little bit here with the truth tables. Now, the conditional is a logical compound statement in which the statement P, we usually use P's and Q's with the conditional. The statement P is called the antecedent, implies a statement Q, which is called the consequent. And I'm sorry to use that obnoxious language with you, but I'm going to have to use that obnoxious language with you a little bit here in this unit. So the right here, the P with an arrow to Q is the symbol saying if P, then Q. In other words, if the antecedent, then the consequent. So in other words, if it is raining, then there are clouds in the sky. Makes sense, right? This is P is raining and Q is clouds in the sky. Now, if the antecedent is false, if P is false in any way, it doesn't matter what the consequence is. It's completely irrelevant. So if the antecedent is false in any way, then the consequent is completely irrelevant. So here is the truth table for the condition. Okay. And because the consequent being false and the makes the sorry. get it together. Because when the antecedent, when the if P is false, then it doesn't matter what the Q is, so they just call it always true. So the only thing that is truly false for a conditional is when P is true and Q is false. Other than that, it doesn't matter when P is false. Does not ever matter when P is false. It's always true anytime P is false. The only time the conditional is false is when Q is false. Okay, so the only time, I'm going to write that. The only time the conditional is false is when the Q is false. In other words, if I wrote this, that would be my shorthand, like I wrote the shorthand up here. Okay. All right. So let's look at this table right here. I need the and. So the M and. Actually, I'm not going to use the letters here. I'm just going to use A and B. And means that they're in the intersection. So that's a true, false, false, false. So again, it's just my little shorthand here. And then if we do P implies Q, that's a true, false, true, true. Because again, it doesn't matter what P is if P is false. Q, it just doesn't matter. P implies Q. Okay, so come over here and let's look at what we need. We need M and not P implies R. I don't know why I wrote not R here. It looks like I need a not P here. Let me just scribble and make a big old mess, but this is what we're going to get here. We're going to do not P. We're going to scratch that out and get a not P. I don't know why I wrote not R. Okay, so let's get a not P here. So all that means is we're just going to go through here and we're going to change what P's got. And then now we need an M and not P. So an M and not P. This is what we're going to do here. So for the ands, remember the only thing that's true is if they're both true. So we're going to have false, false, true, true, false, 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 right? False, true is false. False, true is false. False, false is false. False, false is false. True, true is true. True, true is true. True, false is false. True, false is false. Just want to make sure you see where all those came from. And now we're going to do this crap. Implies R. And it's going to go in this direction. And let's reevaluate. Everything's true unless it is true, false. Everything's true. So false, true is true. False, false is true. True, true is true. True, false is false. False, true is true. False, false is true. False, true is true. False, false is true. I know it's like it will scramble your brains. Lean on those tables closely and heavily. We're not spending enough time on this and in depth enough for you to you didn't come into this class with a whole bunch of theory to understand this. So we're just scraping the edge. Remember, survey class. Okay. The biconditional is a logical statement in which the antecedent and the consequent are interchangeable. So in other words, P if and only if Q happens. So that is the biconditional. And as you see, for the biconditional, the only time it's true is if they're both the same. If they're both true or they're both false. Are they both true? So, oh, look how nice I wrote that there. Let's do the or real quick. So, uh, A or B means it can be in either one. So that's true, 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 and false. Okay. So let's see what it needs. It looks like we're finding A or B. If or only if, not C. That's what we need. Looks like we need to find not C. So I'll go ahead and do not C first. And then let me go ahead and find A or B. So is A or B? One this way with it. So true, true. They're all true except for two falses. So true, true is true. True, true is true. True, false is true. True, true is true. False, false is false. False, true is true. False, false is false. False, true is true. I hope you're seeing where you can really mess up here. So just take your time. No rush. Take your time. None of this is going to take a whole lot of time anyway. Okay. And then finally, we're going to do A or B. If and only if, not C. This direction, because direction matters. And only when they're both true and both false is it true. So we've got true, false, false. True, true, true. True, false, false. True, true, true. False, false, true. True, true, true. False, false, true. True, true, true. Okay. And then finally, the last thing is this idea of De Morgan's law. And De Morgan's law is the negation of a conjunction, an and, right, is the equivalent to the disjunction, the or, of the negation of the statement of the conjunction. Okay, that sounds really, really confusing, but let's just take a look at this. And this right here means equivalent. Either direction. Okay, that's what this symbol means. All right, so if it says not P and Q is equivalent to not P or not Q. Notice that both of them got negated and the symbol flipped over. Not P or Q is equal to not P and not Q. All right, so that's kind of like that idea there. And then let's see, what do I got here? Running out of steam. Okay, last question. Last example. Which is logically equivalent? Okay. What's logically equivalent to this statement? For Valentine's Day, you did not get your sweetie flowers or candy. Okay, so let's make a logic statement here. Let's do F is got flowers. C is got candy. And if we want to write, you did not get flowers or candy. That's what that notation there is. Now, the way to decide which one is logically equivalent is to decide what it would need to be. So to be logically equal by De Morgan's law, which is what we just figured out, not F or C would have to be not F and not. It doesn't look right. Not C, right? Because you flip it over and you change it from an or to an and. So we went from an or to an and both things are negated. So let's see which one is that logically equivalent to here. This one says you did not get them flowers or did not get them candy. So that's not flowers or not candy. So that one's not it because that's not logically equivalent. This next one says you did not get them flowers, not flowers and not candy. Not flowers and not candy. There it is. Just for the fun of it, though, we could write got them flowers or candy, and that's not it either, right? Okay, so that was logically equivalent, and that's why that was helpful for me to turn this into symbols and get it equivalent that way. Okay, I suggest you print out this page. I will be providing you on the final exam with these tables and also a couple other things from the Unit 1 test, right? Okay, well, I hope you guys have a good day. Thank you very much.